Let's let our constant be equal to c. So f of x is equal to c for all x in this set A. Let's take a look at a smaller example where A has just 3 elements, 1, 2, and 3, and we'll take our constant is equal to 1. And we'll use these circles to represent the domains and ranges of our function. So our starting domain consists of 1, 2, and 3, and we're mapping from A to A, so we map to 1, 2, and 3 here, and then again to 1, 2, and 3, except our output after we apply f twice is 1 always, so we're only going to map to 1 here. So for example, if I draw this arrow from 1 to 1, this corresponds to f of 1 is equal to 1. And when I apply it again here, it maps correctly to our c equals 1. We could also have 2 mapping to 1. This means f of 2 is equal to 1. And then we have f of 1 equals 1, so we'll travel the same path to our final value 1. We could also take this path, mapping from 3 to 2. This corresponds to f of 3 equals 2. And we have that f of 2 is equal to 1, so this is going to map to 1 again. So it seems like there are 2 methods to reach our constant. We're going to have some f of x that is equal to 1, and then f of x is also going to put us at 1. That's what we have in the blue and brown arrows here. Or we could have an f, for example, going from 3 to some other number that's not 1, in this case 2, and then when we apply it twice, we have f of 2 is equal to 1, so there's an extra step. It seems like we have to have f of c equal to c, so let's try to show this, and without loss of generality, let's just say c is equal to 1. This means, according to the problem statement, f of x is equal to 1 for all x in our set A. And so then we'll take our input x equal to our constant, which is 1, which means f of 1 must be equal to 1. So of course this works if f of 1 is equal to 1, because then f of 1 is f of 1 is 1. But is it possible to have something like f of 1 is equal to 2, and then f of 2 takes us back to 1? So it works going forward. F of 1 is f of 2, which is 1, but it needs to be true for all x in A. So let's try f of 2. F of 2 is 1, and f of 1 is 2. We need to have this double function always be equal to our constant 1. So this is a contradiction, and we must always have f of c equal to c. So now we ask, how many other values of x in our set A, this is where x is not equal to c, do we also have f of x equal to c? Let's start with the simplest. Can the answer be equal to 0? And again, we'll look at a smaller example where A has just 4 elements, 1, 2, 3, and 4. And we'll try to draw this out. Here is our domain A with 1, 2, 3, and 4, and it also maps to A. And let's take our constant equal to c, so everything has to map to 1. We showed earlier that f of c is equal to c, so 1 maps to 1. Let's see if we can have a path to 1 by mapping the remaining numbers in our domain to these 3 same remaining numbers. So for example, we can map 2 to 2, and then maybe map 3 to 4, and 4 to 3. As always, we have f of 1 is f of 1, which is 1. Let's try f of 2. F of 2 maps to 2. So this is f of 2. And again, f of 2 maps to 2. Here we don't get the output that we want. Next we'll try f of 3. F of 3 maps to 4, so I'll replace this with a 4. F of 4 maps to this 3. Again, not equal to 1. And then we'll have the same thing with f of 4. F of 4 is 3, so this is f of 3. And f of 3 is 4. Also not equal to 1. So basically, for x equals 2, 3, and 4, there's no exit strategy that takes f of x back to 1. So we need to have at least one other of f of 2, f of 3, or f of 4 that is equal to 1. So for example, if we have f of 3 is also equal to 1, then we can have f of 2 is equal to 3 and f of 4 is equal to 3. And so f of 2 is equal to f of 3, which is equal to 1. And likewise here. So now we're going to do casework on the number of values of x such that f of x is equal to our constant. And we note again that the number of these values x is going to be at least 2. We'll always have f of c is equal to c plus one more value of x. Our first case will let the number of values of x such that f of x is equal to c. And let's let c be equal to 1, for example, to make this easier to count. Let's say that out of the 7 in our domain, exactly 2 of them have f of x equal to 1. If our constant c is equal to 1, then we know that f of 1 is equal to 1. And without loss of generality, let's say that our second x is x equals 2. Such that f of 2 is also equal to 1. With exactly 2 of our x's in our domain mapping to 1, the rest of them are going to map to something else so that when we take f of x, it's also going to map to 1. All these remaining values of x in our domain must map to 2, so that when we take f of, for example, f of 4, this is f of 2, which is 1. Now we're going to count the number of ways that our function can conform to this. So for example, we have 7 possible values for c. Given any value of c, we know that f of c is equal to c. This gives us 6 remaining values in our domain, one of which is also going to be equal to c. So this is like 6 choose 1. And the remaining functions in our domain all must equal 2. So this is just one way. In total, there are 6 times 7, or 42 ways to define our function in this case. Let's have the number of x's in our domain such that f of x is equal to our constant, for example, 1. Let's say we have 3 of them. If c is equal to 1, we must have f of 1 is equal to 1. And then we pick 2 more. So we'll just, without loss of generality, pick f of 2 and f of 3. This is 6 choose 2 for the remaining 6 in our domain. And then we have the remaining values in our domain, f of 4, 5, 6, and 7. If we map these to either 2 or 3, when we apply f a second time, we're going to go back to 1. So let's count this. Again, it's 7 choose 1 for our value of c, 6 choose 2 to pick the 2 other values in our domain that are also going to map to c. And then each of these functions independently can be either 2 or 3. So that's 2 to the 4th power. This is 1680. And we'll go to the next case where the number of values of x in our domain such that f of x is equal to our constant, for example, 1 here. Let's say we have 4 of them in our domain. We must have f of 1 equal 1, and then we pick 3 more. Without loss of generality, we'll make it 2, 3, and 4. These are also going to map to 1. And then we have 3 more, 5, 6, and 7. These are going to map to either 2, 3, or 4. So 7 choose 1 to pick our value of c. Of the remaining points in our domain, we choose 3 of them out of 6. And then we have 3 choices for our remaining 3 values in our domain. So that's 3 cubed. This multiplies out to 3780. And we'll go on to the next case. The number of x's in our domain such that f of x is equal to our constant. If it's 5 now, again, f of 1 is going to be 1 always. And then we have 4 more values. F of 2 through f of 5 are also going to be equal to 1. And then we have f of 6 and f of 7. These are going to be equal to anything from 2 to 5. And counting, it's 7 choose 1 for c, and then 6 choose 4 for the remaining numbers in our domain that map to 1. And then we have 2 more numbers in our domain that can independently map to 4 different numbers. So that's 4 squared. And this is 1680. Let's have 6 numbers in our domain such that f of x is equal to 1. We'll pick in our domain the numbers 1 through 6 are all going to map to 1. And then our last function, f of 7, can be anything from 2 to 6. So 7, 6 choose 5 for these. And then we have 5 choices for our remaining element in our domain. This is 210. The last case is when we have f of x is equal to 1 for all 7 numbers in our domain. This looks something like this. C can be one of 7 values. There are just 7 ways to define our function in this case. Let's add everything up. We have n is equal to 42, 1680, 3780, another 1680, 210, and 7. And we want the mod 1000 residual, and we'll combine a few of these terms, and our answer is 399. If you'd like me to solve any other math contest problems, please leave them in the comments.